All right, people are trickling in. Excellent. Sorry about that. Okay. I just want everyone to make a comment in the chat so I can take roll from there because there's no lab report for this week. Okay, we're up to 20. Excellent. People are finding their way in. Either with the new one. Okay, I don't know what the deal is. Okay, we're at 25. Okay, we need to get started, I think. Good, 30. Okay, where am I? All right, so the first 2 weeks of labs is actually what we would normally do. First week, we do the introduction, sorry, to a review of uncertainties and error propagation. And then we do the second week, introduction to the equipment that you would normally use all quarter long. And since you're not going to be using equipment, we felt it just was important to see the equipment anyway. This way, you know, in some future physics class you're in, you can't say I've never seen an oscilloscope before, right? You'll at least have to say you've seen it once. Okay, so we'll go through it here. Let me share this document with you. That's not what I wanted. I wanted this. Okay, and this is the breadboard. This is used for assembling circuits very quickly. And the way it works is these are connected internally. So there are 5 holes sort of in a vertical column here. Those are connected internally. So any 2 wires you stick in there are now connected together. If I have a wire coming from here and another one from here, you can see that these 2 are now connected together because they're in that same column. Those 5 rows there, those 5 inputs are now tied together. The ones below are also tied together internally, connected electrically, but they're not connected across that center divider. That isolates the top from the bottom. So these are connected in this, what I'll call vertical orientation, but across the bottom, there are 2 rows, horizontal rows, that are connected this way. So this whole row is connected together, and the one right above it is connected. Those are all connected together internally, but not to each other. And the same with the 2 up on the top here, right? Those are connected together. The ones underneath it are connected together, but they're not connected to anything else. Now, Let's take a look. I'll run this video that we had here that's linked from the website. I talked you through part of it, but these are really nice for putting a circuit together quickly. So we had a student a few years ago whose father was an electrical engineer. He worked on toys mostly, anything with sound. His expertise was sound. And he had these, we took a tour of his workshop. He had these all over the place, wires hanging out and chips and resistors and capacitors. And he would very quickly, you could assemble a circuit without having to solder anything. And then you could quickly pop a resistor out, pop a different one in, change out components. And then when the circuit did exactly what he wanted it to, he would document it, write it all out, and send it off and have a computer chip made that it would go inside some kind of toy that would make sound. So, so these are quite useful for assembling circuits quickly. Okay, so we want to watch this part of this video. I talked you through part of it. We don't need to watch the whole thing. Let's see, where are my documents? Circuits. If you go into an electrical engineer's worker section, in the lower section are designed, I have power along this whole, it's connected here. Now I have power along this whole row. And so that's why the horizontal, what I'll call the horizontal rows, are all connected together. You can plug a power supply into your leads here. One of them will be ground, that grounds this whole row. So any place you want to ground in your circuit, you can tap into that. And then you have your power being supplied to that whole row. So any place you want power, you can tap in there. And I can tap in anywhere. If I want power over here, I can tap in. If I want it down here, I can tap in here. This is all connected together, and I have power along that whole row if I put. Is this being shared? You good with this video? Okay, good. Power to this input. This one is connected to the other side, so that would be my ground or my the low voltage across, but they are, of course, are not connected to each other. Connected, but they are not connected to any of their neighbors. So these 5 are connected internally, these 5 are connected internally, but those are not connected to each other. And these are connected, is connected to the lower half. That divider electrically isolates both parts. So these are connected together down here, 1, 2. If we hook up the high voltage part of our power supply to this part of our breadboard, the current will flow in to the breadboard here. So let's tap into that. Now I want to go through a resistor. So I'm going to pick one of my resistors. So you can see these two are connected. They're in the same column here. So they're connected internally to one another. And I'll go through another resistor now. And then through a third resistor. And then we'll go back to the power supply. So the current will come in from the high voltage part of our power supply. It would go through this wire. It's connected internally to the left lead of this resistor. So the current would come through the resistor in this direction. These are connected together. You can see right here, those are connected together, and the current would go through the second resistor. And these are connected together right here. Current comes through our third resistor, and that's connected to this red wire, which brings the current to this upper line, and that's connected to the low voltage end of our power supply, which completes the circuit. Okay, so let's go back to our document. So breadboard, that's the gist of the breadboard. It's just there to help you put together a circuit quickly and easily. Okay, and you saw how quick I could just put the resistors in, pull them out, change them out, right? Very quick and easy. Okay, let's move on. Digital multimeter. That's this guy right here. This is what a lot of people call the Swiss Army knife of electrical instruments. It does so many things. It's sort of a marvel of electronics. So it can be used to measure voltage. That's electric potential. The units are volts, but we often just say voltage. Then there's this Greek letter omega is the symbol we use for ohms, and ohms are the units for resistance. So that's electrical resistance. So it measures electrical resistance, capacitance, and A is for amperage or amps. That's current. So it measures current, electric potential, and resistance. And the main dial here, it's set to off right now. That's not only our on-off switch, that is our function, that selects which function we want to use. With this one, maybe I'll just go to the video since I can zoom in on that a little easier. And I'll just talk through it a little bit along the way. This is a digital multimeter. It's a marvel of electronics. We can use it to measure so many different capacitance, just to name a few. Switch, now it's set to off, you can see. But it also picks the function that we're measuring voltage. So you can see there's two different voltage measurements here. The one I'm pointing to in the video has sort of a little sine wave over the V. That means you're looking for AC, or alternating current. You're looking for a voltage that's changing sinusoidally in time. The one next to it has a straight line, a flat line across the top. That means you're looking for a DC, direct current voltage. That's a constant voltage in time, like a battery would put out. And if you look up in the display next to the zeros in the display, there's a V for volts or electric potential, so you know what you're measuring. And right next to it, it's a little fuzzy, I know, but it says AC. So it's trying to measure an alternating current signal, something that's changing in time. Now, if a signal is changing in time, this is a digital display. Are the numbers just constantly changing? You wouldn't be able to really use this for anything then, would you? It is looking for a sinusoidal curve, and it's doing sort of an average. It's not a real average, because what's the average of a sine wave? 0, right? Half the time the sine wave is above 0, half the time it's below 0, half the time it's positive, half the time it's negative. So if you average out a sine wave, you get 0. So what this does, what we do with electronics, is we say we square the whole signal, so that way everything's positive. Then we average it. Then we take the square root. It's called the root mean squared, the RMS value. So this displays the RMS value of the voltage. So even though the voltage is changing sinusoidally in time, this would just display a single number for the voltage if you were set to AC. So it's set to DC. You can see the corresponding DC in the display. Then on this multimeter, there's a third setting over here called millivolts. The third one says millivolts. So if you're measuring a small voltage, you would use that, and that gives you more digits in the display, so you get a little better resolution. Now it can be used for both AC and DC. You'd use the yellow button up above. That yellow button is sort of like a second button, and it lets you switch between AC and DC here. Okay, let's move on. Millivolts, ohms. So if we want to measure resistance, we could do that with this measurement here. One thing to note when you measure resistance is that well, let's just move on. We'll talk about that later. Current is units of amps. So that's why it has an A there. AC amps. And the horizontal line tells us we're measuring DC amps here. You have to be careful with this multimeter. It requires a different input for some of the things we're measuring. So the common input, the reference, is the same for everything. But if you're measuring volts, question about the yellow button. Anytime, if you look at the dial right here next to the A, there's something in yellow there. I can't quite make out what it is. And the one above the A, there's something next to it in yellow. And then if you look up at the top next to the millivolts, there's something in yellow. The yellow button switches into that. It's like on your calculator, you have that second feature. So each button on your calculator actually does two things. So you push that and it tells you you're going to be switching to this other function. Or ohms, we use this input. And if we're measuring amps, we use this input. The digital display gives us a lot of information. This particular unit auto scales. So if I put it on ohms and measure a resistance that's very small, it'll give me a number 50 ohms. But if I put a 50,000 ohm resistor on there, it'll still read 50 here, but then it'll say kilo ohms on the side here. So you have to be careful when you're using it, make sure you know what scale it's set to. Right now, the OL means it's over limit. It's too big a number because there's nothing connecting here. This is an infinite resistance. Let's measure the resistance of a few different resistors. So you can see I'm putting my input in where it's asking for the ohm measurement. I'm set to ohms, and I'm going to use, these are very convenient for snapping onto a wire, clipping onto a wire. And this looks like a 10 ohm resistor. There's also a color code on these resistors. We'll talk about that a little bit more later. It's about 300 ohms. And I'm being careful to keep an eye on the units here. It's telling me I'm going to find one that's a little bit bigger, slightly larger resistance. And it says 0.9, but you have to be careful because it's auto-scaled, and now it's reading in kilo ohms instead of ohms. So this is 0.9 kilo ohms, which is 900 ohms. Okay, So this multimeter we can use for measuring all kinds of different things. And we're talking about resistors right now. Resistors, there's this color code that's printed on them so that you can actually see the value of the resistor just by what's printed on there. I think let's just bring up the video. It's easiest. I'll stop and talk when I need to. All of these resistors have a value on them indicated by this color code. This one is brown, black, black. We know to start from the other end because gold or silver tells us the tolerance. So we'll start at this end and we get brown, black, black. Each of the numbers 0 through 9 are represented by a color. As you can see here, black corresponds to 0, brown 1, red 2, all the way up to white being 9. The gold and silver are for tolerances, although some of the other colors can be used to indicate tolerance also. The resistors we use typically have 4 stripes. The first 3 are for the value of the resistance, and the fourth one is the tolerance. And in our cases, it's usually gold or silver. Those are the 2 worst tolerances, and that's usually what we buy for our student labs. They're the least expensive resistors. Some resistors have 5 stripes or some even 6. Both the 5 and 6 stripe resistors give you 1 extra digit in the value of the resistance and more information. But the ones in our lab typically 4 stripes. The first stripe represents the first digit in the value of the resistance. The second stripe represents the second digit in the value of the resistance. And the third stripe is a multiplier, so 10 to that exponent. So let's take an example. Our resistor was brown, black, black. Brown is 1, so we would have a 1 for the first value of our resistance. Black corresponds to 0, so we'd have a 0 for our second digit. And black, our third stripe, corresponds to 0, so our multiplier would be 0, 10 to the 0 power. So what do we get? 10 ohms. And double checking with our DMM, we get 10 ohms. This one is blue, red, brown. It's possible that the camera is not doing a great job of capturing these colors, but even when you look at them directly, I can assure you that some of these colors are very hard to tell the difference between. Remember, we're trying to come up with a color for every digit 0 through 9. So we need 10 distinct colors. And sometimes it's hard to find 10 distinct colors. When I look at these, sometimes the blues and the purples look the same. Sometimes the black and the brown look the same to me. Sometimes red and orange look the same to me. So it's a good idea to double check them against the multimeter. Our second resistor was blue, red, brown. Blue corresponds to 6. Red corresponds to 2. Brown is 1, so we would have a multiplier of 1. So 10 to the first power is just 10. So 62 times 10 is 620 ohms. Let's check that on our ohm meter. And we get a value of 636 ohms, a little off from the 620 that was marked, but within the 5% tolerance. Okay. So we've seen the DMM and resistors and how to read them. One thing that is normally we would have you do in a lab if you're playing with a multimeter is to measure resistance of your body, right? Just grab one of those leads in each hand and see what the resistance is. Your bodies are slightly conductive, right? Our bodies are slightly conductive. That's why electricity is dangerous to us. If our bodies didn't conduct electricity at all, then electrical signals couldn't hurt us, right? They couldn't pass through us and hurt us. Our bodies typically have resistance in the mega ohm range, so it's pretty high, mega ohms, million ohms, but they do have some slight conductivity. In fact, most or a lot of the biological functions of our body, nerve signals, signals to muscles to tell them to contract, signals to your heart to tell it to beat, are electrical signals. So it's very important that our bodies conduct electricity because of that. Okay, low voltage power supply looks like this picture here. And it's used to produce constant voltage signals, so like a battery, but we can dial this in to be any voltage we want up to the maximum. So they're quite convenient. I'll bring up the This is our DC power supply. It provides a direct current power source, which is like a battery. That means the voltage is constant in time. When you plug something into the wall, you get a voltage that's changing in time. It's actually a sine wave. But this puts out a constant voltage like a battery does. So if we turn it on, we get a readout here, volts and current. Now, the little red light next to the current tells us that we're current limited. There are two knobs here. We want to be controlling the voltage, not the current. So if we're current limited, this is there as a safety. So we turn it up a little bit until that red light goes off. Now we're not current limited anymore, and it's set to 5 volts. We can change that. We can increase or decrease this down and up. Let's go to 15. Now it's putting out 15 volts. We'd plug in to our connections here. And the red one, the positive one, it's indicated on there as positive. The red or positive side is the higher voltage side, and the reference is the black or the negative side. So the red one is 15 volts higher than the black or negative side. The positive side is 15 volts higher than the negative side. Let's take a look at this simple circuit. My DC power supply is powering my breadboard, and I just have one resistor here. And so my DC power supply tells me it's putting out 10 volts and 0.05 amps, 50 milliamps. So let's hook up my multimeter set to DC voltage. And it also tells me that I'm getting 10.03 volts across that resistor. Now, if I change my voltage, first I'll go down a little bit, 6.6, and my multimeter agrees. And if I go up, 14.9, 15.02, they're pretty, oh, there we go, 15.0, 15.0. So to at least the first decimal place, they agree. Now let's take a look at current. To measure current, we have to, first of all, change the input to the current input, change our function to current, DC current. A is for amps, that's a current measurement. And then we have to disconnect something in our circuit. So I'm going to unplug that wire there, and I'll reconnect it through the meter, because the meter has to be hooked up in series. So I'll put this on my resistor, and the current will go through my circuit, through the resistor, through my meter, back to the power supply. So my meter is now in series with my resistor. And you can see that the current here says 0.05 amps, and the current here is 0.048, 0.047, so they agree to the number of significant figures that are available. If I change this up or down a little bit, now we're at 70 milliamps, and if I turn it down, about 20 milliamps. So when you're using this meter to measure current, you have to be in series with whatever you're measuring current with. That means you have to disconnect something in your circuit and reconnect it through the meter. To measure voltage, you don't have to do that. You have to be in parallel. So that means you can just reach in and clamp onto the circuit. But don't forget to change the input and the function settings prior to doing that. And then you just reach in and clip on to measure the potential, the electric potential, the voltage. Okay, so we're working through here. And that's our DC power supply. But sometimes you don't want a DC signal. Sometimes you want a signal that changes in time. So we have this function generator. Now the function generator has a whole bunch of buttons across the front here, these black buttons that you see. And the ones on the three on the very right-hand side, all the way at the end, those control the type of signal it puts out. Is it putting out a sine wave? Is it putting out a sort of a sawtooth wave? Is it putting out a square wave? What's it putting out? And all the rest are for controlling the frequency. How fast is that wave changing in time? So we'll take a look at that next. This is our function generator. Sometimes we don't want the signal to be constant in time like our DC power supply puts out. We want the voltage to change in time, like a sine wave or a square wave, and that's what we use this for. The buttons over here can be pushed to select a sine wave or a sawtooth wave or a square wave. The buttons over here are there to select the frequency. How fast does that wave change? So you push one of those buttons. That's 100,000 hertz. But you can see those buttons are pretty far in between. 1,000, 10,000, 100,000 hertz. This wheel is the multiplier. So right now it's set to 1. So this is reading 100,000. But if I turn it to a half, it's a half times 100,000 or 50,000. If I turn it up to 2, it's 2 times 100,000 or 200,000. So it's a multiplier. So between the wheel and the buttons here, you can get any frequency you'd like. The frequency, again, is how fast that signal is changing, how many cycles you get per second. So in addition to those controls, we can also control the amplitude. So we can turn that down or up, and that controls the peak-to-peak voltage, how much voltage we're getting out peak to peak. Across the bottom are various outputs and inputs. The ones that we use are the two on the right. We typically just use this one. This is the high voltage output. The other output also works for most of what we do. Those are the same thing. One is limited to a slightly lower voltage. The other one will go up to 20 volts peak to peak. So there's our output. Here's our control for the peak-to-peak voltage, and these controls for frequency and our multiplier. This is an oscilloscope. It shows us how the voltage is changing as a function of time. So if you remember, we had a DMM that would measure voltage, but it was mostly useful for measuring DC voltage, where it's not changing in time, and it'll just give us the value there. Or if you set it to AC voltage, it will give you what's called the RMS value, the root mean squared value, which is kind of an average of the changing voltage. But it doesn't really tell you how the voltage is changing in time. The oscilloscope shows you on a nice graph how the voltage is changing in time. The horizontal axis is the time axis. The vertical axis is voltage, or electric potential. This one has two inputs, channel 1 and channel 2, and they're controlled with these knobs. So once the input signal is being displayed, you can use these knobs to change the scale, and it'll scale it up or down. And the other knob here on where it says horizontal, that's for changing the scale in the horizontal direction, the time axis. So there are a lot of controls here that I don't want to get into right now, but these digital oscilloscopes are really nice. The main thing you want to take from this is we've got two inputs. We've got some controls here to change the display. So how does it going to look on the display? Scaling it up and down, things like that. And the other thing you want to know is up here in the corner, there's a button called Auto Set. And that button helps dial in everything. Sometimes you get a little out of whack, and the controls are off, and you don't really get a nice clear picture here. Just push the Auto Set button, and it'll get you really close to where you want to be. It dials things in about where it thinks you want to be. It may not be exactly where you want to be, but once you get close, you can change things with the other controls ever so slightly. It's a lot easier to understand what's going on with the oscilloscope when it's hooked up to a function generator. So we've got our output from our function generator coming to our input on the oscilloscope, and we're seeing a signal on the screen here. Now let's play with some of our controls. So the function generator right now is set to sine wave, but we could change that to a sawtooth wave, and we get this nice triangle sawtooth wave. And we can change that to a square wave. We can change the amplitude. That changes the peak-to-peak voltage we see here. So we can turn it up, we can turn it down. And if it's low like this, and we want to expand the scale, we can use the controls here to make the scale smaller or larger. Right now, my function generator is set to 1000 hertz, and I've got a multiplier of 1. So the frequency should be 1000 hertz. We can look on our display, and it's telling us the frequency is about 1,000 hertz. And if we increase this to 2, the frequency increases to about 2,000 hertz. And you can see we're getting more cycles in the same time period. And if we increase it even more, we get more cycles in the same time period. The frequency is higher now. But if we want to spread this out, we can change the time scale on the oscilloscope. So now we can zoom in and see the cycles a little more clearly by changing the scale. And maybe your scale is just way off and you don't know where your signal is. Just push the auto set button and the oscilloscope will bring you right back to where it thinks you want to be. You might want to fine-tune this a little bit, but it'll get you very close. So we select the frequency here, the multiplier to fine-tune it, what type of wave we want, the amplitude, and it displays on the oscilloscope voltage on the vertical axis, that's electric potential, and time on the horizontal axis. Okay. So it's a lot more fun to be playing with this stuff yourself. I realize that. This is not very exciting. But the important thing is, next time you're in a physics class or an engineering class and somebody asks you if you've seen an oscilloscope or a function generator, the correct answer is yes, you have seen it. All right, so the idea here is you understand kind of that we've got this equipment. Just keep it in the back of your mind how it's that we have equipment that measures these different things. And this week, nothing due. We're finished for today. Nothing due. I'll take roll from the. This is just a pass, no pass lab. I'll take attendance from the chat room. So if you haven't made a comment yet, make a comment. Make sure I know who you are, and then that's it. So I'll stick around. I'm going to pause the recording here. I'm having trouble getting these to record. I don't know why. Every time I do a lab, it says it fails. Luckily, that's not happening for the lectures. So I'm going to stop this recording. We'll